Our home in the cosmos, the Milky Way, is a place of breathtaking scale and complexity. It is a barred spiral galaxy, a colossal swirling city of stars, gas, and dust. At its heart lies a supermassive black hole, Sagittarius A*, around which everything elegantly pirouettes. The galaxy itself is comprised of several components: a central bulge, a vast stellar halo, and the component we call home, the galactic disk. This disk is where the majority of the galaxy's younger stars, including our Sun, reside. It is a relatively thin, flat structure, yet it stretches some 100,000 light-years across. It's a dynamic and vibrant neighborhood, teeming with the raw materials for new star formation. Imagine this disk not as a solid, rigid plate, but as a fluid, dynamic river of celestial bodies. It is composed of multiple arms, regions of higher density where stars are born in brilliant stellar nurseries. The Sun is located in a minor arm, known as the Orion Cygnus arm, about 27,000 light-years from the galactic center. This position is rather fortunate, placing us far from the chaotic and high-radiation environment of the galactic core. The disk is not uniform. Its density varies, creating a complex gravitational tapestry that influences the motion of every star within it, including our own. Understanding this structure is the first step to comprehending our own journey through the cosmos. The stars within this disk do not simply travel in perfect circular paths as planets might around a single star. Their orbits are far more intricate, shaped by the collective gravity of billions of other stars, as well as vast clouds of interstellar gas and enigmatic dark matter. The Milky Way's disk is where the action is, a place of constant motion and gravitational interplay. It is within this sprawling, flattened structure that the story of our Sun's epic voyage unfolds. The disk is both the racetrack and the gravitational engine governing our star's trajectory through the vast emptiness of space, a journey that has been ongoing for billions of years. This grand structure, this spinning disk of light, is constantly evolving. Stars are born, they live out their lives, and they die, enriching the interstellar medium with heavier elements. This process fuels the next generation of stars and planets. Our Sun is just one of billions of stars partaking in this grand cosmic ballet, its path dictated by the gravitational contours of our galaxy. The scale is almost unimaginable, a celestial dance on a canvas of space-time. It is a reminder that we are part of something truly immense, a single note in a grand galactic symphony that has been playing for eons and will continue long after we are gone. Our Sun is on an incredible journey, a vast orbit around the center of the Milky Way. It travels at a staggering speed, approximately 230 kilometers per second, or about 500,000 miles per hour. Even at this immense velocity, the distances are so profound that it takes the Sun roughly 230 million years to complete one full circuit of the galaxy. This period is known as a galactic or cosmic year. To put that into perspective, the last time the Sun was in its current position in the galaxy, dinosaurs were just beginning to roam the Earth. It's a timescale that dwarfs human history, reminding us of our fleeting moment in the cosmic calendar. The Sun's path is not a simple circle, it follows a more complex, elliptical trajectory, much like the planets in our solar system but on a galactic scale. This orbit is governed by the gravitational pull of all the mass contained within the Sun's orbital path. This includes the supermassive black hole at the center, the dense central bulge of old stars, and the combined mass of all the stars, gas, and dark matter in the galactic disk. The Sun's orbit is a delicate balance between its immense forward momentum and the relentless gravitational tug of the galaxy's core and disk, a dance that has kept it on a stable path for billions of years. This orbital motion has profound implications. As the Sun travels through different regions of the galaxy, it passes through areas of varying stellar density and interstellar medium. These encounters can subtly influence the solar system. For instance, passing through a denser spiral arm could theoretically increase the flux of cosmic rays, or even perturb the Oort cloud at the edge of our system, potentially sending comets hurtling towards the inner planets. Our journey is not a solitary one. We are constantly interacting with our galactic environment, a dynamic interplay that has shaped the history of life on Earth in ways we are only just beginning to understand. The stability of this orbit is crucial for life on Earth. A more erratic or eccentric path could take us into the hazardous regions near the galactic center or fling us out into the desolate voids of the stellar halo. Instead, we reside in a relatively calm, stable orbit within the disk. This has provided the long-term environmental consistency necessary for complex life to evolve and flourish. Our sun's grand tour is therefore not just an astronomical curiosity, it is a fundamental part of the story of our existence, a testament to the intricate and finely tuned nature of our cosmic home that makes our world possible. The sun's journey is not confined to a flat plane. As it orbits the galactic center, it also oscillates up and down, bobbing through the main disk of the Milky Way like a horse on a cosmic carousel. This vertical motion is a fascinating consequence of galactic dynamics. The sun is currently moving upwards, north of the galactic plane, and will reach its peak altitude in about 14 million years before gravity pulls it back down. This entire up and down cycle, a vertical oscillation, takes roughly 60 to 70 million years to complete. We cross the galactic plane, the densest part of the disk, approximately every 30 million years. This wobble is driven by a simple yet powerful gravitational principle. The mass of the Milky Way's disk, all the stars, gas, and dust, is concentrated along its central plane. When the sun's orbit carries it above this plane, the collective gravity of the disk pulls it back down. As it gains speed and overshoots the centerline, it travels below the plane, at which point the gravitational pull reverses direction, tugging it back upwards. This creates a perpetual oscillation, a gentle gravitational bounce that adds another layer of complexity to our star's long journey through space. The force responsible for this vertical motion is not just from the stars we can see. A significant part of the gravitational pull comes from dark matter, the mysterious substance that makes up about 85% of the matter in the universe. While dark matter is thought to form a large, spherical halo around the galaxy, models suggest it is also concentrated to some degree within the disk itself. The precise density and distribution of this dark matter influence the strength of the gravitational tug, and therefore the period and amplitude of the sun's vertical wobble. Studying this motion provides a clever way to map the distribution of mass, both visible and dark, in our galactic neighborhood. This periodic crossing of the galactic plane might have tangible consequences for our solar system. The plane is the densest region of the galaxy, and passing through it means encountering more interstellar clouds and potentially a higher rate of gravitational perturbations from nearby stars. Some scientific hypotheses have linked these crossings to periodic extinction events on Earth, suggesting that the increased gravitational disturbances could disrupt the Oort cloud, sending a shower of comets towards us. While the evidence is still debated, it's a compelling idea that our planet's geological and biological history could be rhythmically influenced by our star's galactic seesaw motion. To truly understand the sun's motion, scientists rely on sophisticated models of the Milky Way's structure. These are not physical constructions but complex computer simulations that incorporate our best knowledge of physics and astronomical observations. Current models such as the Beijing-San model or simulations from the Gaia mission attempt to create a realistic three-dimensional map of the galaxy. They include the distribution of different stellar populations, the location of gas and dust clouds, the structure of the spiral arms, and, crucially, the pervasive influence of the dark matter halo. These models are constantly refined as new data becomes available. The European Space Agency's Gaia satellite has been revolutionary in this field. By precisely measuring the positions, distances, and motions of over 1 billion stars, Gaia is providing an unprecedented data set for building these galactic models. This allows us to map the gravitational field of the Milky Way with incredible accuracy. By observing how other stars move, how they orbit, and how they wobble, we can infer the distribution of mass that is guiding them. This, in turn, allows us to calculate the sun's past trajectory and predict its future path with greater confidence, refining our understanding of its orbital speed and its vertical oscillations. These models are essential tools for testing our theories about the universe. For example, by comparing the observed wobble of stars with the predictions from models, we can constrain the properties of dark matter within the galactic disk. If the stars wobble more than our models predict based on visible matter alone, it points towards the presence of an additional unseen mass component. It's a beautiful piece of cosmic detective work, using the subtle movements of stars to reveal the existence of something we cannot directly see. The sun's motion becomes a probe, a sensor for mapping the invisible architecture of our galaxy. Ultimately, studying the sun's journey through the Milky Way is about understanding our place in the cosmos. It connects the physical principles of gravity and motion to the grand narrative of our cosmic origins. It reminds us that we are not static observers but active participants in a dynamic, evolving galaxy. The intricate dance of our sun, its grand orbit and its gentle wobble, is a reflection of the fundamental laws that govern the universe on the grandest scales. By unraveling this dance, we learn not just about a star, but about the nature of the galaxy we call home and the magnificent interconnected cosmos of which we are a small but precious part.